class. Okay, dear. So today, what we're going to do is we are going to look at, uh, well, we're going to continue with cache memory. Okay, we've got some time yet left to do. This is the normal arrangement of the cache. Okay, so you've got a CPU, which obviously borrows its um, data from the cache word by word, and the main memory gives a block transfer to the cache right now. So basically, as this happens, because as we have discussed before, that whenever we are looking at instructions to be fetched and so on, we need to sort of try to imagine that which is the next instruction that is going to be fetched. And if we do it word by word, if we do it, just one data unit at a time, that doesn't make any sense because, it is going to be very expensive to do that way, both in terms of time as well as, well, time mostly is going to be very expensive when it comes to time. Now, so what we do is we try to find out wherever the instructions appear, okay, and the blocks in which the instructions appear, we try to take them in from there. Now, the point is obviously that now if you talk about the elements of cache design, we will cover two aspects of that. One is the cache size ratio, and the second one is the mapping of the cache to the memory. And we're going to use the book on William Stallings, book of William Stallings, I mean, book written by William Stallings on computer architecture for this purpose. Now, I hope you can see this. Just try to stabilize it as much as I can. So now, what is said here is that the size of the cache should be small enough so that the average cost per bit is roughly that of the main memory. What does that mean? Then look at the next point. Large enough so that the overall average access time is close to that of the cache alone. Okay. So what does that actually mean? Well, simply because the main memory is larger, much, 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 much larger than the cache. Cache is typically like in some kilobytes, maybe 512 kilobytes or whatever. Okay. Maybe a little bit more than that, maybe 1 gigabyte. Sorry, 1 megabyte. But if you talk about the main memory, you can imagine you have all got computers, so you can imagine what that is like. That's going to be something in the region of 1 gigabyte, 2 gigabytes, 4 gigabytes. My phone itself has a 4 GB RAM. Okay, so computers may have even much larger. So it is very obvious that if you look at the cache here, so it is it's actually quite obvious that yeah, go on, Kostab. No, 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 no. We are not talking about that. That way, that thing is that is a cache basically means a buffer. Cache basically means a buffer, an in between buffer. When we are talking about a web cache, when we are talking about an internet cache, we basically refer to a part of memory where certain things are stored, like for example cookie, like for example certain browsing data other than the cookies, some other administrative data that helps us look at websites, etc. So that has got nothing to do with, well, I'm not saying that has got nothing to do with it because obviously you are implementing a web cache in memory, and what we're talking about here is the actual hardware. Okay, so we're talking about the memory blocks, we talk about cache memory blocks, and so on and so forth. Yeah, it's in the yeah, that's that is that is right. So basically, you have got the physical cache there is whatever 2 MB or 3 MB, whatever that is. Okay. Now, as opposed to that, the main memory typically runs into gigabytes. And for example, my phone itself, small device, contains about 4 GB of RAM. So your computer may contain even more than that. Some phones have 8 GB of RAM. So obviously, you can imagine that when you are trying, now this is a go-between memory, if you like, right? So you're bringing in data from here to here. Obviously, you cannot transfer the entire bit of main memory into here, and that is not also the point. The point is when the CPU tries to access some data, is it available in the cache or not? We want to make it available in the cache as far as possible because the cache is a faster part of memory and accessing it is faster. But at the same time, cache is more expensive because its technology is higher than that of the main memory. The cache, for example, may typically be made out of SRAMs. And SRAM is obviously, as you know, it is made out of JK flip-flops type of sort of registers. So if you want to have an SRAM cell that is far more expensive than the DRAM cells that the main memories are generally consisting of. Now, so in that case, we automatically have that the mapping, there should be some sort of mapping because a large amount of data, a huge amount of data in the main memory is mapped onto a very small amount of data in the cache. So it will not always be possible to bring everything in. But we want to make it available when it is needed. It is just like that. It is like this. If you can think this as a big reservoir. So, this is basically okay. For example, another example. Let us say this is your Kent water purifier, and it has got a huge amount of space available for purifying the water and storing it in there. When you turn on the water purifier, it purifies the water and stores it in the tank. But what you do is you put it in some bottles and make it available in all of the rooms. So your bedroom may have two bottles, your dining space may have two bottles like that. That is actually being taken from here, just like that. So from a larger place of water, you're getting it into a smaller place of water so that it is available to you when you want to drink it or when you want to make some tea or coffee with it, then it is available to you. Similarly, a very large amount of data is made available bit by bit. Yes, well, bit by bit, I don't mean literally bit by bit, I mean in small pieces in the cache memory so that when the CPU needs it, it's there. Now, what I mean by that, that's small enough so that the cost per bit is roughly equivalent to that of the main memory. Is that, for example, if the main memory is say 2 GB and your cache memory is say half of that, say 1 GB, it doesn't make any sense because this being very, very expensive, let's say it is say 5 or 10 times more expensive. I'm just speculating. It may not be that, or it may be more than that. I'm just saying that let us say it is 5 or 10, so 5 times example, for example, 5 times more expensive than main memory. Now, if on the other hand you got 2 GB of main memory but 1 GB of cache, you can bring a lot of data into the cache. But what is the expense? The expense is obviously this is say x and this is x by 2 multiplied by 5. This is x by 2 because this is half of main memory. So x by 2 multiplied by 5, which is 5x by 2. So ultimately your cost becomes 5x by 2 plus x, which is a lot. That's 7x by 2, which is a lot. Rather than that, if you keep it smaller, say for example, as we know that this is typically in megabytes, and this is in gigabytes. What is the factor? See, 1 GB is actually 10 to the power of 3 megabytes. The factor is that of 1000. Okay, so 10 to the power 3 is 1000. So the factor is that of 1000. So this is say, let us say for example, let us say we've got a 2 GB main memory and we've got a 2 MB of cache. So it's 1000 times smaller. So in this case, even though the cost of accessing this is in actuality um, like 5 times more, but how much of cache is there? Only well, we have we've only got like 2 MB, which is like a factor of 1,000 less. So the ultimate cost, it doesn't really matter. What matters is the cost of the main memory because it is such a huge one. So the cost goes into there. The same thing happens, for example, if you have a, say a term, say 9 to the power, say n to the power of 7 plus n. Now you will ignore this because this is a much larger term, right? So for simplicity's purpose, we can just say this term is n to the power of 7 term. Why? Because this is much larger than this. It's just a one constant. So just like that. So that is why we say that small enough so that average cost per bit is roughly equivalent to that of the main memory. But on the other hand, if you make it too small, for example, instead of 2 MB, just make it say 20 kilobytes of cache, what will happen? The thing is that you will look for some data in the cache. It is not going to be there because it is only 20 kilobytes. So how much of data can it store? Not much. So you go in there, the cache memory, and the data is not there. You have to fetch it from main memory. How much can you bring in? Only 20 KB of data. And what is the size of the main memory? 2 GB. Now this time around, the factor is that of 1 million. Okay, so 10 to the power of 3. So basically, you have got 10 to the power of 3 KB is equals to 1 MB, and 10 to the power of 3 MB is equals to 1 GB. So you see the factor is 10 to the power of 3 multiplied by 10. So that's basically factor of 1 million. And so look at what will happen. You will be forever trying to. And last time we talked about hit and miss, cache hit and miss. You will be forever trying to put a cache hit in place because every time you're going to look for a data, it is not going to be there in the cache. So you have to go into the memory, fetch the data, go into the memory, fetch the data, go into the memory, fetch the data. Not very conducive to proper computing. It will not be very conducive to your computing needs. Okay. So that is why there has to be an optimal size. But there is one thing though, that smaller cache means the lesser number of gates that are required in accessing. Okay, because the cache logic, you see, is such that it maps on some data in main memory to the cache. Mapping on something to the cache, obviously, you can imagine it requires some selection, some operations on it. All of this is required, and that is happening, or that happens through gates. Through because this is a digital circuit. Come on, this is just a digital circuit. What is it made out of? AND gates, OR gates, NOR gates, NAND gates. This is what it is made out of. So the smaller is the cache size. Okay, the lesser is the cost. The lesser is the number of gates. And that obviously means that that also comes into the sense that there are lesser number of gates means it's a lesser number of circuit complexity or lesser circuit complexity, and obviously lesser amount of money required to implement this. But at the same time, it has to be large enough so that it can accommodate enough data so that there should be minimal number of misses. But the point is that you see that the optimality of size is basically very difficult to achieve because the cache performance is sensitive to the workload. What do I mean by that? Or what does the book mean by that? It's actually from Starling, as I say. So what does the book actually mean by that? See, when a program asks for data, now on Friday we did spatial locality of reference, we did temporal locality of reference. Now when you are talking about that, when you are talking about the program using some sort of a data, then what is the spatial locality of reference? You've got to consider that. What is this temporal locality of reference? You've got to consider that. That means how many instructions are there which are bunched together? How many jump instructions are there? The more the jump instructions, the lesser is the spatial locality of reference, and hence the cache performance will dwindle, and that means it will go down. Now let us look at say loops. The more there are loops, the more we would want to put the loops in the in the cache, because that would be temporal locality of reference. But if you use a lot of loops, which includes a lot of like very complex loops. Like for example, if you have say nested loops within nested loops, and so on and so forth, tree-level nesting, and so on and so forth, you have a bit of a problem in your hands. Because as discussed on Friday, what you want to do, you want to put all these uh, the code for the loop inside the same inside the cache, ideally inside the cache, or in the upper parts of the main memory. By upper parts, I mean parts that are closer to the CPU. So if there are levels, say M1 to Mn, I am calling these to be the lower part, larger in size but much slower, and these are smaller in size but larger. So you want to at least put it in the highest level of main memory, which is directly accessible by the CPU. Why? Because if it cannot be brought into the cache, then at least it can access it from M1 and then put it into the cache. But the point is that will your loops be completely contained in this space? It depends totally upon what the loops are. Eventually, if you have very, very large loops, there is no way you'll be able to put it all in cache. See, mind you that cache is actually being used by other programs also. It's not just this one program with a lot of loops. Other programs also using the cache. So when you are loading such a very big loop, it may not be totally accommodated in cache. Some of it may remain in say the say M1 levels or whatever, and if not possible, then in M2 levels, like that. And then it's a problem because then you have to move the data forward and backward. So depending upon the how, or rather, I should say like this, depending upon how the data is arranged, especially when we are talking about locality of reference, the spatial and temporal locality of reference that are afforded by the program, that affects the size of the cache. So it is very difficult to maintain an optimality. So we go for rule of thumb that okay, keep it in such a way that it is not too high, it is not also too low. If it is too high, then it will be expensive. If it's too low, then also it will be expensive in terms of accesses and stuff. Okay. Now, when you are now, so how does the now this was about cache size. Now we come to how this is mapped on to this. Now we obviously know that for several lines of main memory, there is only one line of cache. How many? Let's say a rule of thumb. If you have, say, if you have 2 to the power of, say, if you have 2 GB of RAM, that's what? 2 to the power of 3 MB. And if you have, say, 2 MB of cache, that's just 2 MB. That means for every 1,000 lines in main memory, you have that has to be mapped on to what? One line in cache. Okay. So that means that all the time there are so many um, different lines which map onto the cache. Now, what is the arrangement of the cache in this sense? Look at the arrangement of the cache directly from the book itself. Okay, this is how it is. Okay, this is main memory. Var 1, 2, 3, 4, 5. This is cache. And how is it arranged? The entire block contains different words. Can you understand this? Please tell me if you have not. So anyone who has not understood this, see, once again, these are the various lines. So this you see the block of keywords. This is main memory. Now, when it is transferred to cache, you cannot do that. You cannot just transfer this keywords like this because there are not so many rows. So the cache memory is made in such a way that in one row you can put in keywords. And you may say, sir, in that case, how can we retrieve the words? Well, obviously there are functions for that, as we will see in a minute. But let us say, suppose that this is word 1, word 2, like that. There is word k minus 1 and there is word k. Now, if we can locate the line in which the word was stored, then we can also use the cache selection logic to select the particular number of bits that we want or bytes that we want. So these are k bytes and these are all addressable in cache. So let us say we can say that line number 1 and line number 1 is maybe it contains the 32 words. Let's say 32 words. We can say something like this: line number 1, word number 15, line number 2, word number 16. We can say that. So this way, what is happening is the this particle arrangement is mapped onto this horizontal arrangement, and we can get it from there. And we can get it from there. Just like it is just exactly like if this was your phone and you could not see these sides, you stop, you just get it out of rotation lock and you just tilt it around, do it sideways. So you've got a wider view. That's what we do in the phone. That is what they do in the cache memory also. Is this what clear to everybody? Ayush, Prachi, and okay, Nikita, okay, and Rohan as well. Okay. Now, how do we map this onto this? There are three basic types. One is a direct mapping, one is an associative mapping, and one is set associative mapping. Before I go into the intricate details of these, let me just explain them to you in plain English. In direct mapping, so just one sec, just one sec. Hang on just one sec, please. Give me a second. Okay. So in direct mapping, you see the so these are the data in the main memory, and we're trying to bring it into cache. Now, the function is used on direct mapping function is used on this in such a way that it maps onto some unique number. The data that is contained in there maps onto some unique number based upon the places of zeros and ones. It is divided into tags, word line, and so on and so forth. So see in a minute. But so the entire data is rather sorry, the entire address is divided into your this kind of. So we have got a tag there, you got a line number there, you got a word number there, etc., etc. So that each memory address, because it is directly done on the memory address, right? Now, memory address is obviously constant, is it not? When you are making the memory, you have 2 to the power of n minus 1 addresses, right? So 0 to 2 to the power of n minus 1. So there are 2 to the power of n lines in this main memory. Addresses are obviously 0 to 2 to the power of n minus 1. And this is fixed, isn't it so? Is it fixed or is it not fixed? Is it dynamic? Anona? Just one second, Gulsop. I've asked Anona. Yeah. Sorry? Is it fixed or is it dynamic? You think? No, there's nothing like I think. Dynamic. So you mean to say that memory addresses are dynamic, physical memory addresses are dynamic? So this is the main memory chip. Is it growing or shrinking? Something like that. So see, I'll come again. There are 2 to the power of n lines. Okay, so basically this is an n bit word. Okay, small n bit word. Small n bit word means there are 2 to the power of n combinations. So there are 2 to the power of n combinations. There are 2 to the power of n lines. These are from you start from 0. So the highest range is 2 to the power of n minus 1. Is it not? Okay. So is that fixed or not? Good. It is fixed, obviously, because this is the hardware. So there are all these addresses. Okay. So Kosta, you are saying something? Yes. So it is fixed. Now, according to the direct mapping functions, these are the lines. So some of these addresses will be mapped onto this. Some of these addresses will be mapped onto that. Some of the other addresses will be mapped onto this, like this, and is always fixed. Because these are fixed and the functions work on the memory addresses, the mapping of this into this is always fixed. So whenever you are looking at something in the cache, you compare the address, look up the cache. If it is there, bring it into the CPU. Bring it into the CPU. Oh, that's fine. What happens if you do not have it? Well, then you go to the main memory. You get it as keywords into the line there. And those keywords can fit into this line very easily. So there you are. It's as simple as that. So direct mapping. So that is because all the addresses are directly mapped to one line. Money. I'm saying that a bunch of addresses is directly mapped up to one particular line of memory in cache. So this is the direct mapping. What is the problem with the direct mapping? Let us suppose say 0 and let's say 10 and let's say 20. Let us say that these 0 and 10 and 20 all map onto this. Let us say the first line. Okay. Now you see, let us say that a program is using 0 and 10 and 20. What will happen? If 0 is there, 10 is not there. This is say the block 0, if this one, it is the first block, mapped onto this. If this is there, then this one is not there. And if this is there, the other two are not there. If this is there, the other two are not there. And if a program, unfortunately, or a group of programs, unfortunately, at the same time try to use this, this, and this, then you will forever be having misses. It won't be there. If 0 block is there, the 10 block is not going to be there, the 20 block is not going to be there, 20 block is there. So each time you look for the one, the other two are not going to be there. So you'll be constantly throwing some data back into main memory or transferring back, transferring forward, transferring back, transferring forward, transferring back, transferring forward. Understand? This is the main disadvantage. This is a very easy thing to do, direct mapping, but it's a very disadvantages also because of this particular reason. Do you understand this bit? Good. So, has everybody understood this direct mapping and its disadvantage? All right. And obviously, if you don't have, if you can't understand it now, or if you have a read through it and can't